Alright, we're going to finish up this SI worksheet with 10 through 11. So number 10, give the major organic products A through D of the following reaction sequence. I want to highlight something before I start this problem. These diols are added to aldehydes or ketones as protecting groups, but there's some selectivity to how they add. So what they're influenced by is the partially positive charge on the carbon in the aldehyde or ketone. So up here you've got the carbon that's attached to a carbon with 3 electronegative atoms like chlorine or bromine or fluorine, and then an H. So this carbon is having its electron density pulled away by the oxygen in that double bond, but also by this group right here, this electron withdrawing group. So that's a really pronounced partially positive charge, and it's really reactive. As you move down this list all the way to a ketone, the partially positive charge is still there as the oxygen is withdrawing electron density, but it's not as pronounced because you've got a little bit of electron density being added by these carbon groups. So as you go down, an aldehyde, like a formaldehyde, is more reactive than an acetaldehyde, which is more reactive than a ketone. So that's going to play a role in this problem. It says give the major organic products, and you're starting with one equivalent of this protecting group, this diol protecting group. So it can only react with either the ketone or the aldehyde. And we just showed that the acetaldehyde right here is more reactive than the ketone. So it's going to react with the acetaldehyde. So you're going to get this product right here. And then H2N and H2 you might recognize from the Friedel-Crafts acylation, where you follow up that acylation by cleaving off that carbon-oxygen double bond. So that's what's going to happen. And so this is your product B. And then HCl, some aqueous acid, is going to cleave off is going to remove that protecting group for us. So you're coming back down to your aldehyde. And then in product D, you're following that with NaBH4, which is a reducing agent that will reduce an aldehyde to an alcohol. So you come down, and this is your D product that's formed. So that's number 10. Moving down, number 11 is pretty similar to that, and so we'll go through it. Product A, you're going to add a protecting group to this aldehyde. And so it's going to look like this. And then Mg ether and CO2. I'm going to combine all this into one step. You've got you're forming a Grignard reagent, and you're following that with carbon dioxide, or dry ice sometimes it's written, but that is going to form a carboxylic acid. You form the Grignard reagent, and then you take that Grignard reagent and you form a carboxylic acid out of it. So product B, you're going to have the carboxylic acid, and then you still have that protecting group on there. And then you're following that with some aqueous acid, so you're going to remove your protecting group. And so you have that aldehyde back there, and you still have your carboxylic acid up here. And then you follow that with NaBH4, which is a good reducing agent for aldehydes and ketones, but it won't reduce a carboxylic acid. So the product that you end up with is this carboxylic acid and this alcohol right here. So that's your product D. Number 11. Okay, last problem in this drill set is a synthesis for these two reactions. So I'm just going to walk you through the synthesis that I already drew out, because it's just really time consuming to draw the whole thing. You're starting with this diol, And the cool thing about the first synthesis is that it's making you think of this product. This is the protecting group. So you're kind of thinking about the protecting group's perspective here. So you can take the protecting group and you can add it to, let's say, acetone, and you can form this. Like the acetone can add on. You're essentially forming a protecting group for the acetone. And then you've got that bromine, so you can make it a Grignard reagent and have the MgBr there, and then you can use this product to attack another acetone, and it'll attack like we saw and form an alcohol. It'll attack one time, but there's not a good leaving group on this acetone, so it's only gonna react once, and then you're gonna need to follow that with an aqueous workup so that you can protonate that oxygen, and then you can follow it with just kind of that acid workup that cleaves off the leaving group, and you'll wind up with your protecting group back here, but you've altered it, and then you'll get the group that you protected, that acetone, out of it. So that's the way I did the first synthesis. The second synthesis, you are starting with two carbonyl groups. You've got an ester over here and you've got a ketone over here, but remember that these diol protecting groups are good for aldehydes and ketones, and so they're going to be a lot more they're going, like, this is only going to react with the aldehyde or ketone. It won't react with the ester. So you form your protecting group here, and you're left with this ester that's opened, and then if you reduce that ester with lithium aluminum hydride down to an alcohol, you can remove the protecting group with a little bit of acid, a little bit of aqueous acid, and then that aqueous acid will be just enough kick to do that ring closing step that we talked about before. And so the product here, this alcohol group, will attack this carbonyl carbon, and it'll do a ring closing step, and you'll form this hemiacetal product. And so that's my mechanism for the second part of number 12, and that's the SI sheet. I hope that it was helpful. Best of luck studying.